Hello and welcome back. This is the first video of section 14.2, which will in general cover the calculus of vector valued functions. So what we're looking at here are how to make sense of derivatives of these vector valued functions and integrals of these vector valued functions. So we'll start in this video by just introducing the definition of a derivative of these vector valued functions. And then we'll come up with an easy way to compute these by using your knowledge of derivatives of single valued functions. And then we will go through the geometry of what is actually coming out of this derivative. Like, what is the geometric interpretation of the derivative? Let's get started. So first off, what should be the definition of the derivative of a vector valued function? So maybe it's helpful to first refresh our memory for a single valued function. So this is single variable, single real valued function. So just put in a scalar, get out another scalar. These are the things that we studied in Calc 1. And remember the derivative of this, f prime of x, well, we got this by comparing the rates, the difference in the output compared to difference in the input in some way. So we define this as limit as, I'll say, delta x goes to 0 of f of x plus delta x minus f of x. So that is a little change in the value, the output of the function, divided by, so we sort of normalized it by delta x. And remember that if our function described, say, the position of an object, the derivative outputted the velocity. Also remember that this was the slope of a tangent line at x, whatever this value is here, right? X or a or x naught, whatever. It gives us the slope of the tangent line at that point. So, right, this is our algebraic definition. This is our geometric meaning for it. We're going to want to look for these two things down here for vector valued functions. So, oh yeah, again, we turn our attention to what should be the definition of the derivative of a vector valued function. Well, I want to set it up in much the same way. So let's say I have r of t, and this is my vector valued function, vector valued r of t, and it's equal to, say, let's say f of t, g of t, h of t. Remember, my vector valued functions are really made up of three scalar valued functions for each of the components. And then, so I want to do the same thing. I want to compare the change in the output compared to a change in the input. So on top here, I want, let's define this thing, r prime of t. R of t, let me put a prime on it, r prime of t. Let me write that a little bit better so that we're all clear on the notation. So here I have my arrow, r prime of t. Well, so this should be the limit as little change in the input, right? That's like my delta x goes to 0. And then again of a change in my output over that time frame, or parameter change, minus r of t, all over delta t, the change in time. So right, it might be helpful to come back to this idea of position to velocity. So if r is telling me the position of an object, this top portion of this would represent just the change, the change in the output, the change in the position of it, and then divided by how much time it took to make that change, right? So this gives us velocity. More on that in a bit. So let's see. As delta t goes to 0, so how do I want it? Well, I have these three functions here, and I know how limits work with vector valued functions, so let's go ahead and actually use these. So I'm going to do that minus that. So what I'll get here on top, so I'll still have this limit as delta t goes to 0. And so I'll have f of, so I'm going to put this in component form. So I'm going to carry this 1 over delta t with me. So that's a scalar, and that's going to be scaling a vector, right? Because r is written as a vector, or can be written as a vector. It is a vector. And I'll have f of t plus delta t, right? Because I'm evaluating this vector valued function at this value of t. So that's going in for each of these t's here. G of t plus delta t, and h of t plus delta t. Minus, and here's why I like to use the whiteboard, because it runs over. And then I'm taking away just whatever the vector is at t. F of t, g of t, h of t. So we can, and 1 over delta t for the whole thing, so that's that change written out in vector form. I can actually do that difference. So this is what, limit delta t goes to 0. I still have my 1 over delta t. And now I'll have the vector. And you know what, actually, I'm going to distribute. Remember how scalars work? I can distribute them into each component. I'll keep that there for now, but I'm going to distribute that in when I make this move, because it's going to highlight something I think is important. So I'll distribute that 1 over t through, and I'll have what? F of t plus delta t over delta t. Oops, did you catch that mistake? It should be f of t plus delta t. And then I'm also going to do this subtraction here, minus f of t. I'll do the same for g, so just combining the two vectors I have up here and multiplying through by 1 over delta t. So that's g of t plus delta t minus g of t over delta t. And then I'm just going to say dot, dot, dot here. Same thing for h. And we're taking limit as delta t goes to 0. But remember that I can, as I discussed at the end of the last section, end of 14.1, we can distribute the limit through to each component as well. So actually, I'm just going to, we'll do that on the next line. So what do I get? I get limit, I get the vector, which is limit t goes to 0 of this quantity f of t. I keep doing that, I'm so sorry. F of t plus delta t minus f of t all over delta t. I'm going to say dot, dot, dot for the rest. Same thing for g, same thing for h. We'll have a limit in each one, right? Limit t goes to delta t, or t goes to 0 rather. Sorry, delta t goes to 0. Delta t goes to 0 here, and a limit is delta t goes to 0 in the rest of the vector. And we should be recognizing each one of these components now, right? This is the derivative of f at t. This will be the derivative of g at t, and this will be the derivative of h at t. So I get out f prime of t. This is a vector. G prime of t, h prime of t. And we uncover a very important fact about derivatives of vector valued functions, and that is the derivative of a vector valued function is done component wise. It's the derivatives of each of the components. So we say, right, these vector valued functions are differentiated component-wise. So this is true for derivatives. It's also going to be true for integration. We'll get to that later on in the section, but this is how it works out for differentiation. So great, right, that means it's easy for us to calculate derivatives of vector valued functions because it's reduced to computing derivatives of scalar valued functions, which we are familiar with. All right, so what's the geometric interpretation of the derivative of a vector valued function? Well, it's the tangent vector. So what is a tangent vector? We know about tangent lines. Tangent vector is going to point along the motion. Remember how our curves, when we have these vector valued functions, they trace out curves, and those curves have orientation to them. Remember back to that video where I talked about this? The tangent vector is going to go in the direction of that. So it's actually going to be a vector, and this is very cool. So let me jump to one of our interactive figures in the text. So just to look at what geometrically is going on when we're computing these various portions of the definition of the derivative, right? So here's our R of t. It traces out a curve that looks like this, right? Nothing special. What we're really focusing on here is what's the geometric interpretation of this difference quotient. So we'll take it kind of step by step here. So here's R of t, and then R of t plus delta t just means I'm now over here on the curve, so I know I have a direction to the curve, right? I'm over here, and right, and I can change my delta t, right? I can make it smaller and smaller and smaller, or I could make it really big. But remember, we're going to be thinking as delta t goes to 0, so I'm going to want to think of this on small scales. It's also going to be helpful to look at it as it goes from like 1 to 0.1. Here is my smallest delta t that I can sort of imagine. That'll be the most helpful. And then we can compute the difference of these two. So remember what the difference of these two is going to look like is a vector here pointing back at from q back to p. Or sorry, rather from p to q, right? R of t plus delta t, right? Sorry, from p to q. Right, so that's that vector. That's my difference vector, and I can look at that as my delta t gets smaller and smaller. And as it should, if my function is continuous, it should be that the limit as delta t goes to 0 of just this, the difference vector, should go to the 0 vector, right? As long as it's continuous, that should happen. And so that's not too interesting to just look at the limit as delta t goes to 0 there, because it'll just go to 0. But rather, if we scale this by the change in the parameter, right, to get some notion of rate of change. So now I'll look at the scaled version, that's the red one, and compare that to just the change in the vector. So I'll move it down to 0.5 again. Notice how the change in the vectors, the difference vector, is getting smaller, but the red one here, my rate of change is not getting that much smaller, right? And as I go to 0.1, it's still this size. So it's actually, as delta t goes to 0, as long as this function is differentiable, each of its components is differentiable, we'll end up with a vector here as I take delta t to 0. And I can actually do that here in this interactive figure, which is pretty cool. So I take delta t goes to 0, and I end up with this vector in the limit. Now that goes along, it points in the direction of motion, and it's tangent to the curve at that point. How neat is that? So, and remember, algebraically, what's going on when we actually compute this is we're taking the derivative of f, the derivative of g, the derivative of h, and we're putting those together into a vector, and what comes out is this vector here, or rather this vector function, because I can do this, right, at any value of t, and it'll always point in the direction of motion, and give me an indication of sort of how fast it's moving along the curve, right? I can also think about speed and things like this. So very cool. We now have three-dimensional derivatives. So very exciting day for everyone as you're watching this. Let me jump back here and just uncover these guys. So just kind of going over what I just said. Points in the direction of the curve. Oh, here's a little caveat. What if the derivative comes out to be 0? Well, then we're talking about the 0 vector, which doesn't have a direction. So at that point on my curve, my vector, I'm not moving anywhere on the curve, right? My change is exactly 0. So there is no direction to the motion at a point like that. That's pretty weird. Anyways, we call this the tangent vector. That's r prime of t. Remember that, again, it's helpful to think back to this sort of physics example, position to velocity, that we did so much in Calc 1. Same thing true here, right? If we have a vector that's describing our position, then the derivative of that will give me the velocity. And that velocity, again, should point in the direction of motion. That's exactly what a velocity is, and tell me how fast it's moving, right? Speed and direction, that's velocity. Right, okay. Let's do one example here of just computing some derivatives, and I'm not doing a separate video for this example because, well, it should be really easy for us at this point. You might have to remember some derivative rules and things like that. Don't be afraid to jump to earlier chapters in the book. Remember, like 1 through 5, that's sort of what we're referencing here, because if I do, say, r prime of t, I want to find the tangent vectors to r, I just take a derivative. So I can think of it like this. Derivative with respect to t of t cubed if I want to write it out like this. You don't have to. And then derivative with respect to t of 3t squared times derivative with respect to t of t cubed over 6. That's really what we're doing. And so I get out, what, 3t squared and then 6t. And then these are all just power rule, right? We should, try and remember this. Sorry, I don't mean to shame anyone that maybe doesn't remember it. I hope that you remember it. If not, it's okay, right? I don't mean to shame you, but what that means if you're not remembering how to do these basic sort of power rules is you got to go back and refresh your memory. Send me an email, right? Come see me, help get some help on that because we're going to be doing that, right, a lot. This all sort of depends on your knowledge of Calculus 1. And that is the tangent vectors. That's the derivative of r. Pretty cool, huh? We can do the same thing down here, r prime of t. So derivative of e to the minus t, remember your chain rule. Derivative of the inside is a -1, so that's... I'll write this in IJK form like I'm given here. I could write it in vector form as well. It doesn't matter. So this will be minus e to the minus t in the I direction. Plus, I have 5 over square root of t, right? Remember that this is the same as 5 times t to the -1/2. So hitting that with a derivative gives me, what, -5/2 t to the -3/2. Oh yeah, remember these rules and remember what powers really mean. These are coming back. They're back in style. They're always in style. 5/2 t to the -3/2 in the j direction. And finally, derivative of cosine of 3t, right? Chain rule, the 3 is going to pop out, so we'll have 6 times, what's the derivative of cosine again? Minus sine. So I'm going to have minus 6 sine of 3t. And that's in the k direction. All right, that is it for this video. Right, we've seen some good stuff. We can now take derivatives of vector valued functions and understand what the output is telling us. All right, we'll work some more examples and keep uncovering more with derivatives of vector valued functions in follow-up videos. I'll see you there.